Lesson 712 is called the central limit theorem, and the whole idea of it is, well, from what you've done before, we looked at how we can find, with Bernoulli trials, the probability of getting a certain number of questions correct out of 10 with 5 choices. And that's what this top table is. And then you graphed it on what looked like this little curve along here was already on the paper. Okay, and that little curve represents a normal curve. It's the normal curve when the mean was 2, so there's the mean, and the standard deviation was the square root of 1.6, which we use Bernoulli formulas to find both those. And you can see, well, the bars don't match the curve exactly. They're really, really close. So the idea with the central limit theorem is we can actually use a normal curve to approximate a lot of probabilities very quickly and easily. So what I wanted to look at with this example is how do we get our calculator to show a normal curve, to show a normal probability distribution function. So we looked at, this was from a previous lesson, we found the mean for one roll on a dice, the variance of rolling a dice one time, and so if we're looking at the sum of 4 rolls, our mean was additive, so we can just take 4 times our mean for one roll, and we get 14. So 14 is our expected value for the sum of 4 rolls. And our standard deviation, well, that's not additive, our variance is. So that's where the 4 times 35/12 comes from for 35/3. And then our standard deviation would just be the square root of that. Okay, so if we go to our graphing calculators, we can get a graphing calculator to show a normal curve and to show it as a graph. First thing we'll do is we're going to go to y equals. Okay, and I'm going to clear out anything that's there. And this is a distribution. Okay, so distribution is on the virus keys. It's distro. Okay. What we're doing today is a normal PDF, normal probability distribution function. So I'm going to go ahead and select enter for number 1. And if you have the updated software, it's going to give you a screen that looks like this. The X value is the idea, what particular value are you looking at? So we're going to call this X for now, so it can find different values. Our mu and mean are the same thing. So in this case, our mean value is 14, and our standard deviation is the square root of 35/3. And then we're going to go to paste. So that's been pasted into our Y1. Now, if you don't have the version where it pastes it directly in, I'm just going to try to arrow so you can see the whole screen. Some of you might have a version where it says normal PDF, and then you would just have to make sure that as you entered this in, you looked at the particular sum, comma, the mean, comma, the standard deviation. You just enter it in that format. Okay, so we're looking at certain sums here. I'm going to set the window so you can see it a little better. The smallest our sum could be if we're looking at rolling 4 dice is 4, because you could get 4 ones in a row. I'm going to make the X minimum just a little bit smaller than that so we can see the whole picture and make it 0. Our X maximum, well, if we had all 6s, that would be a sum of 24, so that's the biggest we could ever get for a sum. I'm going to make it 25 again just to see the whole thing. XCL counted by 1s, that seems reasonable. Now, this whole curve finds probability. Our smallest probability is 0. That's an event will not happen. Our biggest probability could ever be is 1. That's 100%, it will happen. Our Y scale, I'm just gonna make that be 0.05 so it matches the graphs you've seen. So if we go to our graph, okay, and it'll take a little bit to graph. See, our curve is very, very tiny because our graphs, our probabilities are much lower than 1. So we could go back to window, and instead of making our y maximum be 1, I'm just going to make it 0.5. And that's just to kind of zoom in a little bit on our graph. And just like we could trace on any graph, we can trace on this probability distribution function. So if I go to the trace button, we want specifically the probability we get a sum of 14. And according to our calculator, it's about 11.1168 if we round. So here's the probability. We get a sum of 11 from our probability distribution function or normal curve. And I figured out what the actual probability was using some things that were looked at in lesson 7.3. And the actual probability of getting a sum of 14 is exactly 0.1127. So you can see that these two values don't match exactly, but they're really, really close. And it was a whole lot faster to graph this normal curve than it would be to list all 6 to the 4th possible ways to get sums and find the probability by hand.